everyone for joining us for our Data Insights workshop. We are super excited to get this workshop started. We kind of thought, right after the hackathon, this would be a really, really awesome event for everyone who attended that event, as well as some of the coworkers that you have on your team, maybe having the same issues as you, or some of your colleagues that you've shared this with. So we're really excited to have you on, and thank you for taking your time to spend with us. So I'm going to introduce myself really quick. If you were at the hackathon, you'd probably remember me. My name is Ruti Senanayaka. I do all the events, PR, social media, any type of marketing for Blueprint. And I've been with the company about 2.5 years, and I really, really love working with this team that we have from Precisely and our Blueprint team to produce events that are super beneficial for our attendees. I will now have our 3 presenters and speakers give a quick intro about themselves. First of all, Dan, can you give us a quick intro on yourself, please? Oh, looks like you're on mute.
I'm Dan Kernigan. I work for Precisely on the big data team. So what we've done is we've ported a lot of our traditional applications like our geocoder and our routing engine and a lot of our spatial functions into big data. And in this case, specifically Databricks.
Excellent, thank you. And what about you, Corey?
Let me know, am I still muted? Can you guys hear me?
We can hear you.
Perfect, okay. So hi, I'm Corey Hinden. I lead the data science practice at Blueprint, and I've been working with the Precisely SDKs and Databricks for a little while, and they're pretty cool. So we're gonna show you guys some of the stuff they can do.
Excellent, thank you. And Eric?
Hello, everyone. My name is Eric Vogelpohl, and I have the honor and privilege to lead tech and strategy at Blueprint. I've been here for almost 4 years and love it. And thank you to our partner Precisely in the data and intelligence practice area of the company. Things are going crazy right now, and we are so excited to have the ability to stretch into referential and third-party data for enhancement that is Precisely. So welcome, and thanks for being here with us.
Awesome. And now we want to hear from you guys. We want to know your name, where you work, what issues is your organization facing. And I understand not everyone's going to want to answer, but if you are comfortable with speaking, you can even you can unmute and put your camera on if you like, and let us know. I'll give like a couple of seconds to see if anyone wants to talk. If not, we can move on, but we'd love to hear from you.
So I can go. Razi Kased with Eagle View Technologies. My current role is to support the delivery of engineering software development. I have the title of release train engineer, but my background's always been in GIS and data science. And one of the things I know from our organization, and I'm here more on just to learn and develop sort of my skill sets and my understanding. But from our organization, we use a lot of imagery, we use a lot of data, and I can see sort of the enrichment data that's afforded through Precisely as a big resource. But I don't have any specific issues I can share or have to point out. But that's one thing I learned from the hackathon, and looking forward to learning more about how to use that Databricks environment with data.
Excellent. Thanks so much for sharing. Anyone else like to share? That's totally fine. We can go ahead and move on, and I just want to let you guys know this is a very interactive event. So if you have questions throughout, we want you to ask them. Don't have to wait till the end to ask any questions. Just unmute, ask away. We want to make sure it's as interactive as possible. So now I'm going to pass it along to Eric, who's going to chat a little bit about this topic.
Yeah. So why are you likely attending? Well, if you're attending, you're the coolest person on earth. So that's reason enough. But in all seriousness, as we kicked off the hackathon, I'll share some thoughts and even some findings that some feedback that we had gotten. You know, we're in this era now, era 3 or 4 or something. Maybe we should give it a number. I don't know. Where look, a lot of companies are starting to exhaust the capabilities of insights that can be derived off of data that their own transactional systems or customer management systems or product systems contain within themselves. And we are rapidly in a world now where third-party enrichment data, particularly with respect to human activity and socio-demographic and census and risk management, you know, human movement information can be a 10x, 100x force multiplier when combined with the data that you have in your warehouses or on premise. So, you know, if we're at this crossover period now where organizations that have reached a point of perhaps diminishing returns to additional insights derived from just the data that you have within the context of your systems, now's the time to start thinking about joining that up to data sources that precisely provide the stair steps that you can take in insights derived, again, with respect to product, customer, store, location, etc., by geolocating your data are immense. Now's the time to master these skills. And that's exactly why we put the hackathon and these workshops and any subsequent workshops that we want to put together. So again, thank you for being here.
Thanks, Eric. Now Corey is going to get into the real meat of the presentation along with the other presenters. I do want to mention that I shared a login link for you guys to hop into the Databricks environment and follow along as Corey is showing these. But feel free to let me know if you have any trouble with that, or you can even just unmute and say if you have any trouble while you're going through things. You should have received the login information and the link. So thank you guys, and take it away, Corey.
Sure. So before I dive deep into this, I just want to get a quick just view. Okay. So if for participants here, right? So we've got some Blueprint people precisely and stuff, but what I can spend time talking about code, or we can spend time talking more about architectures and ideas and kind of gloss over the code a bit. I'll, for now, I think with my assumption right now, I guess, is I'll not go too deep and heavy into the code until somebody asks, but we will be seeing the code. But I just want to make sure we're talking to the right audience here. So, and here comes the lawnmower, so all right. Okay. So, if you're familiar with the hackathon, right, we basically posed, here's a bunch of data, come up with a problem and, you know, define it yourselves so we know what you're trying to do and solve it and show us what you did. So what we did in Blueprint is we took just a little team of 2 1/4 data scientists, and we said, all right, same thing as the hackathon, you got 2 weeks, see what you can put together, and then we'll share it with everybody else. So problem statement, let's keep it kind of fun. Here we go. The Starbucks C-suite has recently become obsessed with online ratings of its stores. In an effort to drive up the critical executive KPIs like average online rating, AOR, they have decided to build a new location somewhere in Tennessee. As Starbucks data science data engineers, your team has been tasked with choosing the best site in Tennessee to build a new Starbucks to drive up this metric. So the constraint being, you must finish this POC in 2 weeks or the executives will have moved on to a new priority and forget about the project entirely. So a little fictitious scenario here, just to kind of give us a business context and setting for what are we doing, and as we build all this code and this pipelines and everything, why are we doing this? What's the goal? So, and just as Ruthie said, thoughts, comments as we go through, feel free anytime. We'll keep this pretty casual. We've got a lot of time set aside for this, so I don't want to, don't want to waste time on the wrong things like some particular Spark code implementation of something when it may be more interesting to talk about, bigger pictures with someone. All right. We do have a slide in here. I think someone else wanted to grab this one before we bring up notebooks.
Sure. So the software tool that we used from Precisely in this hackathon was part of our data integrity suite. We have ported 4 of our software categories into Databricks. So we're capable of doing change data capture from any platform, streaming that into a Databricks environment like the Delta Lake. We have governance, data integrity, which is data quality and governance and matching capabilities that run natively in Databricks. My particular area is specifically around location intelligence and data enrichment. So 3 of the tools we used in this hackathon were our geocoder and address validation tool. Our second was our location intelligence or spatial tools, and the third was our routing engine. And Corey's going to talk about that in a little more detail next, but the idea behind those is we can accurately and precisely locate an address, apply a Precisely ID, which is a unique and persistent key assigned to that and only that address, and then use that with our data to apply roughly 9,000 different attributes that describe that location that are also tied to that unique and persistent key, making it very easy to join any of the Precisely data or your own data for that matter back to the original address.
Cool. And I'll say this a few times as we get into the notebooks here in a second, but I do want to put emphasis on it's pretty easy to use this stuff. So we've got a team of data scientists. None of us have written these geocoders ourselves before, but with the SDK that Precisely, built and let us use on these clusters, it's pretty simple to do this process and get a ton of more information for our case, right? Training some models.
It's good.
Yeah. Okay. So there's a couple slides here, but I've also got them duplicated somewhere else. So let's just jump into the notebook unless somebody's got any questions or anything before we do that. All right. So yeah, these are the notebooks you should have access to now. We're talking about the workshop notebooks. There's just 4 little sets here. I think there's 12, 13 total notebooks. So let's start here. This is really just high level before we dive into code implementations. What is our plan, right? We've got a problem statement. How are we going to solve this problem, right? So breaking it down with a lucid chart, because we all love these. What are the steps in this process? What are the notebooks we need to write, the tools we need to build to accomplish this task? So let's walk through it real quick. Let's look at the blue first, the light blue. What we're going to do is we're going to get a data set of online reviews. This is available in the Databricks hackathon clusters. We call it the X Challenge review data. It's online reviews. So there's things like text reviews. If someone left a review on a business, those are cool too. But for our executive metrics, we're after AOR, right? Average online rating. We're going to look at the star ratings, right? So we've chosen Starbucks because it's in that data set and sounded fun. So we're going to say, hey, for every Starbucks in this data set, what's the average star review of that location? And we're going to use that data enriched with Precisely data to train a machine learning model to predict the star rating of a new location based on enriched data. So data about that location and the area around it. So high level, the things we do with a Starbucks location, or say we know its address. First is I'm calling it GeoStar. Maybe you guys have a cooler word for it in this world, but to me, I want to geocode each location. I'm going to do some geo-routing, which we'll see some pictures on, which is pretty cool. And then Geofence. I want to find what are all the locations near this Starbucks that I'm interested in. So this is, as you see here, when we get into feature engineering, there are residential and businesses that will come back in these data sets. So maybe I've found 1,000 homes nearby and 500 businesses close to a single Starbucks location. So what we'll do is we'll separate those 2 data sets so we can allow our data science team, we can have multiple team members building engineering features on these sets separately. Once we've built done a little bit of feature engineering with all the enrichment that's available from the Precisely datasets. We'll dump these into just a delta table as training data, and we'll let another team member, when as people have time, right? We jump in and we say, okay, we've got the training data. Let's poke around. Let's see what kind of modeling we can do, and then let's set up a Spark grid search on those models to figure out, hey, what's a good model for this purpose. We'll persist that model and then set up an inference notebook. So that's the blue path. That's the bulk of the work. Once you've got that, the rest of it's pretty easy. The second part to this task is, okay, it's not enough to train a model. We want to make a decision. So what we did is we got some real estate data. We said, hey, we pointed out Tennessee just because that's where I was born, so I picked that one. So I got on one of these real estate websites, I don't remember which one. I said, hey, show me all the business, restaurant, real estate that is for sale in Tennessee today. And there's, I think it was only 20 or so at the time when I ran that query. So a pretty small data set. Said, okay, if I'm Starbucks and I want to build here, then I'm making a choice between these 20-something locations. So I grabbed that data, basically their address and their price. And we pass it to the same machine, the same pipes. All the GeoStar, the Geocode, Route and Fence, the feature engineering, we build all the same features we built for the ML model. We just transform it exactly the same way. And we dump that into Delta table. And then our inference notebook picks that up to make predictions on all the 20-something locations. What would the star rating theoretically be? Or what would we predict it to be? So high level, this is the plan. We can pause for a second here if anybody wants to have a question, comment, oh, it would have been cool if you did this too, or anything like that.
When you say feature engineering, I'm not exactly clear what that means or looks like, or what sort of artifact comes out of that.
Yeah, so good question. So feature engineering, it's probably data science-y lingo kind of stuff. In this case, what we're talking about is let's go concrete example. That'd be easier to understand. Given a Starbucks location, what is the average income in a 5-minute drive time radius around that location? That would be a feature that we engineer for that one particular point. So another feature may be, what is the population in some radius around that point? So we're doing some transformations. We're joining to Precisely data and aggregations and trying to figure out more information to kind of describe the neighborhood around any address.
You could have presumably brought in correlated information from the performance of Starbucks that exists in areas that map similarly to those areas as well. In a sense, increasing the number of dimensions or features in the data that the algorithm bites onto and says, this is meaningful in the prediction outcome that we're looking for. In this case, star rating. Yep. If it's meaningful, if it's powerful.
Exactly. And it's a good context to keep in mind, right? And data science, ML world, feature engineering, there's multiple ways to go about this. And it's kind of neat since we had a team on this, a small team. When we get into the notebooks, you'll see different approaches different data scientists take, right? There's kind of the deep learning approach where you say, hey, throw all the features at it, let the model figure it out, right? It can handle that. And then there's the other kind of more high-level data science-y where it's like, hey, as a human, I understand this problem, right? So I can construct intelligent features that may or may not fall out easily from simple aggregations. So we kind of have the best of both worlds in this that we can dig into. But the big idea is you want to build features that help some algorithm predict what the star rating might be. Now, to be totally clear, just to be upfront with everybody, we'll dig into this, we'll go through it all. We made the conscious decision not to spend most of our time here, because as data scientists, we could live here for months and never get bored, right? You can always make these models better. You can live here for months and never get bored. But what we decided to do was focus more on end-to-end and kind of telling this story of how to solve a problem like this, because realistically, if we became experts in predicting the online review rating and stars of any company, that's not very transferable to anything super helpful, right? The features that help me predict the star rating of a Starbucks, are probably not going to transfer very well to predicting demand or revenue, right? It's a very different problem. So we kind of left it as it's a problem, it's technically solved, but let's not focus all our efforts on being experts at predicting stars, if that makes sense. Okay. So kind of like what we said, and again, did somebody chime in there? Okay. Okay, so kind of like what we said, just keeping stuff high level for now. Our goal here is to build a data set that looks like this. There'll be some Starbucks IDs, however you want to identify them, maybe store numbers or something. We'll have some features. We've not labeled them here because we don't know what they're going to be yet. And who knows how many columns you'll have. You'll just have some features to describe that Starbucks. And then you'll have a star rating that we got from these online reviews. When we can have a data set like this, we're ready to start training models. So this is our first goal. And yeah, so let's talk about how. How do we do something like this? How will we do, right? So to build a table with these types of features, we're going to use location intelligence and data enrichment for each Starbucks location. So let's get through some definitions real quick. And, you know, Precisely is on the call. If I use a word wrong, please jump in. But this is my understanding from the UDFs I've been calling at least. So first things first, given a Starbucks location, this little red dot here, we know its address, or we know something like its address. So we can pass this to the geocoder, and it'll give us a validated safe address as well as a unique PB key. So this is a unique place in Precisely's data set. It's a unique location. We'll get lat long and everything too, so we can easily plot a lot of this, and you'll see some of this in a bit. But this is kind of step one, clean up that data. Step two, when you have that, we'll pass this into the GeoRouter. So what we do with the GeoRouter is we construct a polygon around that Starbucks location, which represents a 5-minute drive time polygon, right? So everything that is inside that polygon can be reached within 5 minutes of driving. So it actually, these polygons are really cool looking. They do not look like this. We'll see some pictures here in a little bit, but it's a pretty neat tool. The reason we do this is for the next one, this geofencing. We want this polygon so we can find every other type of property that exists inside that polygon. This is where we can start to describe, essentially think of it as describing the neighborhood around a potential store location. So, and that's what all these black points are.
And it might be worth noting, and maybe we'll get some feedback from Daniel as well, is just geocoding the data alone, a la data validation or data cleansing of locationable data that you have within your enterprise is value in and of itself. So if you don't extend to all of Precisely's capabilities and reference data that you get once you have geolocated your data, geolocating to a precise location and validating that address is value in and of itself in many regards. Right, guys?
Absolutely. That's probably the biggest use case that I see is address validation geocoding.
Yep. And, you know, to be totally fair, right? We're kind of data science team. We like to get a little nerdy with it and go this extra step, sure. But, you know, with the Precisely data, once you've geocoded, you could directly join, like you can find the census block of that Starbucks and you can get some already aggregated features and you can stop there, right? You don't need to go the extra couple of miles that we did for fun because we like it and maybe we're a little sadistic with writing some code, but you know, that geocoding gets you most of the way there, right? This other stuff is kind of add-on if you just want some additional new features to try to help your models out. So good call out there. All right. So let's talk about kind of like what we just hinted on. What's the next step? So we do something like this. We end up with tables where we're going to have for every Starbucks location, see these three are the same ID, these three are the same ID. We'll have many PB keys. So we'll have many black dots associated with a single red dot, right? There are many locations near each Starbucks. So what we want to do is we'll take this and we'll join each of these black dots to enrichment data. So for example, one of them may be household income, and maybe one of the data sets we're interested in. And we can understand the household income for every single one of these points inside. And yeah, we end up with, you know, some enrichment already, right? Now, in practice, what we do is we join to a lot more than just one. We can have some neat algorithms where we sparsely randomly chose a bunch of features because there's a ton of features to choose from, and we kind of intelligently chose a few, and we'll get into that. But yeah, the idea is basically once you've geofenced, you can start enriching every point inside that fence and get some cool new metrics out of this.
Yeah, I do have a quick question. If you go back up, yep. Just refresh everyone's note. If I've got, says Starbucks ID, store ID, we'll just say location 001, is repeated 3 times in your bottom table because it's got 3 unique PB keys. And the income average, I assume, is changing slightly. What's the intuition of one Starbucks having 3 records?
Yeah, good question. So say we have a Starbucks in near some residential neighborhood. There may be 3 households in that neighborhood, each with different household incomes, right? So this is how they all tie. They're all very close, within a 5-minute drive to the same Starbucks location, but there are multiple houses there.
Got it. So that's household income. And then maybe a further refinement is we would maybe collapse that and take an aggregate, an average, a max, or whatever as we go down the pipeline.
You got it. That's the next step we got here. So as we build, I don't know if my camera's visible, but we have cat company as usual. So yeah, so exactly like Eric was saying, we have our goal, let's not forget, is 1 row per Starbucks store. And I forgot I can't double click that markdown cells. We want 1 row per Starbucks store. Right. So let's aggregate these 3 rows that had 3 different household incomes. Let's perform some aggregates to get a single row per Starbucks, individual Starbucks location. So in the example here, we've taken a mean, but in practice, obviously we have much more sophisticated aggregations than that, as long as we can collapse these down. Okay. So we do this for a bunch of features, and what do we have now, right? Kind of visually trying to keep this high level to understand what's going on. If each red dot is a Starbucks location, we can draw a polygon around it to kind of understand, to help us figure out what other things may be nearby, residential or business. And then we can join those to enrichment data sets and aggregate them to get essentially summarized features about the neighborhood near a Starbucks, right? So the average income per year, how many other cafes are within this drive time polygon, what's the population in this area, right? There's a lot of information we can build about the surrounding area for a single Starbucks point. Okay, so once we have that data set, it's modeling time. So us data science people start getting excited. What's all the cool stuff we can do here? So just to reiterate, for the purpose of this, right, 2-week hackathon style challenge, we wanted to be more end-to-end focused than specific modeling focused. So we left a lot on the table. Excuse me, it's totally okay to say, hey, when we get to the modeling part, you could have done this too. We're probably going to totally agree with you and beg Eric or somebody to say, hey, can we spend more time on this just to see how cool we can get it, right? But yeah, just keep in mind, there's a lot more fun to be had in this space. I will call out, because we're in Databricks, right, we have Spark at our hands. We don't want to just train models kind of naively in serial. So we do have a really simple way, since you're in Spark, basically define a hyperparameter tuning grid, map all those parameters to workers, and train thousands and thousands of models in parallel very fast. This is just a happy Spark environment use case, and we'll see that code too. And then finally, we track all of our experiments, all our model training in MLflow. So at the end, we can just quickly grab, hey, sort by the metric I care about most, give me the best one, and we have the best model that we want to use. So there's a really cool integration with MLflow in Databricks. If you haven't used it, super easy. You'll see that code pretty soon. All right, so at that point, you've trained a model. You go to the bottom half of the plan that we saw earlier, and it's really simple, right? The real estate data that we said, hey, these are our candidates. These are the places we might build our next Starbucks. We just rank them. We predict the stars for each of them, and we rank them based on opportunity, essentially. All right, so that's kind of the high level. From here, we're going to start looking at code, and I would love if people in attendance maybe ping Ruthie or say something in the in the chat. Hey, this code's boring. Talk more high level. We'll go faster. That's totally okay. Or if someone's like, hey, I'm really interested in that algorithm. Can we look at it for a second? Either way is fine. Okay. So preparing model data for the model. So first things first. Here's the old hackathon logo, if you remember this, right? What we're going to use to build our training data is the 600 locations of Starbucks that's in the X Challenge Business Review data set. So they look kind of like this as a summary. There's more data in there, but really there's an address. We know it's a Starbucks if we filter, and we get an average rating for that location. So a quick reminder of where we are in the plan. You are here. Right, we're going to do the GeoStar process. We're going to end up with a Geofence at the end of this notebook. Okay, so straight import, whoops. Anyway, let's take a look. Let's just do some really simple SQL, Spark SQL, right? And let's look at a small sample of the X Challenge Starbucks locations, right? We have business IDs that are unique. We have names, we have addresses. This is going to be useful for the geocoder. Right, I think within our key, we've added this USA as country. This is just to help the geocoder out. And we have the star ratings. So we have, the start of our training data. Here's the stars, here's the location. Now we just need to enrich. We need something to train on because this isn't anything to train on. Okay, so before we can run this stuff, if you did participate in Hackathon, you probably saw the notebooks, but Precisely has notebooks to install the geocoding libraries for you. It's really easy. All we need to do is run their code, and we can just get to use their UDFs, right? It's super simple. Here, I've collapsed it because it's all in one notebook. We can take a peek at it, but here's the Scala code. They've already installed the packages, so these are just doing the imports and defining the UDFs. But from my I want to use it perspective, that's solved. I'm moving on. I'm going to use it. I don't need to know all the details about that part.
A quick jargon check. Quick jargon check. What's a UDF?
Oh, cool. Okay.
It sounds delicious.
Yeah, UDF, user-defined function, I believe. Someone correct me if I got that wrong. But basically, in things like SQL and Scala and Spark SQL and all these things, basically it's a way of defining a function to apply per row in a data set. It can get more complicated than that if you want, but I think that's a pretty good high-level summary. Basically, your custom function applied to every row. Okay, so geocoding a small sample. So we have this data, but just for the purpose of running through these notebooks, we showed, okay, here's if I needed to geocode, if I wasn't doing Starbucks X Challenge data, if I was working for Walmart, and I'm looking at this notebook and I want to use my data here, how would I geocode my Walmart stores as step one? And this is the beauty of how easy it is with the Precisely SDK, right? We basically say, hey, I'm going to take that sample, right, the one we just saw, where I have my not clean address yet, right? Address, city, zip, state, country. And I'm just going to map those into their UDF. Call the geocode UDF and give it the address, city, state, postal code, and country. And that's how hard it is. Like, that's all you have to do. Once you call this UDF, your result, which comes back pretty quickly, is this clean data set. We have the formatted street address, and we have the formatted location address, as well as lat long and a PB key, which is pretty crucial for the rest of this work. This is how you do join it for the enrichment data, further enrichment. But really, like, it can't get easier. It's a one-liner. I broke it up into many lines because I'm a code Nazi or whatever, but it's a one-liner, right? That's as easy as it can get. Okay. So after this step, you've geocoded your data set. One cell in a notebook, you're moving on. So let's do the crazy data sciencey stuff, because that's the guys we are. Let's do the geofence, the georouting and geofence of those locations. This one is it takes a little bit more calculation time. I think we didn't try beefing up clusters super high or anything. We just we knew of all the things in our plan, the thing that would probably spin the longest would be this. So we just kind of said, okay, well, I got to sleep at some point, so I'll just run this one when I go to bed. So no problem. This is easily finished in a few hours for the 600 that we had on a pretty tiny cluster. Nothing expensive. But anyway, so this is just saying, okay, these are the geocoded Starbucks, right? We're going to take these geocoded Starbucks and we're going to do some GeoRoute and geofencing. And just another note here, just like the geocode, the GeoRoute and geofence it boils down to one-liner UDF calls again. This is really easy, right? I don't think I ever wrote a Scala code before I tried to run their UDFs, and I found it easy to write Scala code using their UDFs. So it's pretty simple as far as code can go. So nerd stuff, maybe ping Ruthie if this is something you don't want to see, and I won't go too deep after this one, but what we did to help us with we knew this was going to be an overnight run, or that's how we planned for it. And for big processes, we like to use kind of a batching and checkpointing pattern just to save our butts if we screw something up, right? So we did that with these. We've got about 600 or so we want, so we batched them up and we ran, I think, 25 batches, and we'd persist results into Delta every time a batch finished. So if anything went wrong, we could just pick up where we left off next time. So here are the ones that were probably interesting if you're here. Creating a travel boundary, right? It's literally take a data frame, add a new column, and call a UDF, right? Super easy. It literally can't be easier than this, right? Same for geofence.
And for clarification's sake, you didn't write this code first principle. You didn't have to sit down with a blank sheet and write this. The primers, the starters, the kickstarters all come from Databricks. They all come from Precisely. They're embedded in Databricks. The UDFs are ready to go. This was a start for you, right? A quick start.
Yep. We can just check docs, and we know how to write this line, right? And then we just wrap it in a function so we can have clear code when we're calling it and all that. And super simple. The hardest part about this code for me was that I'm not a Scala developer, so I had to Google, okay, how do I do my type hinting? How do I, literally just the simple basics. This stuff was the easy part. Same with geofence, right? Once you have that polygon column defined, geofencing is just calling another function here, right? So first we filter out null polygons, and then we call this simple function, and we have geofence data. So it's super easy. So even for this this weird data science approach where we wanted to not just enrich, but like aggregate neighborhood enrich, right? It's 2 lines of code gets us to that point. So it's worth, I'd say. And then we just have a little append to delta, blah blah blah. Let's not worry too much about that. Yeah, so here's our little batch processing pattern. Really simple. We've got 25 batches. We have a for loop for every batch, and in the for loop, we get the next batch we want to work with. We create the travel boundaries, we create the geofence, and then we write it to delta. That's it. It's pretty simple. So this one did run for a few hours, but no big deal. If we wanted to go faster, we just beef it up and we'd be there.
Yeah, you could. So just to note, what that's doing is actually a pretty complicated process in the background, right? You have a polygon that represents that 5-minute travel boundary. And then we also have polygons for every address in the United States that actually represent their parcel boundary. So think of that as the lot on which an address sits, which is also described by its precisely ID PB key, right? And what's actually going on behind the scenes is it's doing a intersection of every polygon in the United States. We could optimize it, right? You can put filters in to say, okay, let's not go that far. Let's limit it to just the polygons within the area. You can do that by doing some lat-long mathematics to filter it out. In this case, we didn't, but the point being, there are probably a half a dozen optimizations that we normally do. The biggest use case we get for this, believe it or not, is in healthcare, where providers want to know how far is it from my office to every other doctor's office in the United States. And we end up with this array that's 1 trillion rows.
Wow.
It's quite a complicated process, but that's just the aside. I'm glad we made it easy, Corey, because that was the objective.
Yeah, success.
Fantastic.
And so I actually come from a background. So when you say, hey, intersection of polygons, that is a pretty non-trivial thing just for 2 polygons. So having seen the shapes of these drive time polygons and, the parcel boundary polygons, that's a lot of calculations. And I didn't have to think about any of them, and that's what I'm happy with. All right. So let's take a look at the results of the geofence locations. Just a little note here on precisely IDs. Precisely IDs are unique. And let's see, persistent index applied to all addresses in the geofence. We refer to them in 2 ways in our data files just because we're using PB keys in 2 ways. And this is just our convention. This is not a precisely thing, I don't think. But basically, when you see our tables like this one, this is select star from Geofence Starbucks, right? The PB underscore key is talking about a Starbucks PB key. Without an underscore, we're talking about something in the geofence. Now, we probably could have named differently if we wanted to be more verbose, but this is what we went with.
It's a good idea.
Okay, so here's an example of a Starbucks that has been geofenced, and we found stuff around it. So here's first chance we get to actually see. If you guys have seen GeoPandas, the cool way to make plots like this. But basically, the red dot is a Starbucks, and all the other points are things that we found precisely IDs for within the 5-minute drive time polygon, which is this really cool looking kind of splatter around on the ground. So if you've never seen polygons like this, it's pretty neat. They're all pretty unique looking, and this is I think a relatively small set of points. Some of these geofence results come back with a lot of things nearby. So we plotted one that could be visually pretty easily understood, but there's a lot of data, right? Had we skipped this geofencing step and just gone with, say, the census block of the Starbucks, we would have missed a lot of very detailed information available in this drive time polygon. So we're getting a very different description of the area by doing this. And this is probably the data scientist in me saying it, but we're adding new information here, and our models have a chance to grab onto something else and get some more accuracy.
Corey, based off the superficial finding of additional PB keys or additional geolocated assets within this drive time polygon, they're all blue, meaning I don't necessarily know that you've called out a house or a school or an auto repair shop. Those blue locations could be one of many things, right? They're not necessarily other cafes or other homes, right? At this point.
At this point, they're not, you're right. I don't think we have a plot for that, but it would be relatively easy to put together. But one of the early enrichments that we do, I think one of the next steps is we actually separate all these blue dots into residential and business dots. And then we build our filters separately. Yeah. Cool. So we don't have that picture, but you're spot on.
Corey, I had a question. Looking at the drive time polygon, I'm just curious about some of the edges and how they jut out, sort of in the upper right and the lower left of it. Just trying to understand why are those why does the polygon have those jagged edges? I guess on the edges there.
Yeah, so like this edge here.
Yeah, that one, and then anything on the lower end there. Just curious.
Yeah, so I'm going to take my intuitive guess at this, and feel free to correct me. But so this looks like a relatively bigger road, right? So it's easy to drive this way for a minute or so without having a direct cutoff to a residential or a business, right? There may not be a driveway on this road. You may have to take another road and cut back to it or something. So I think for most edges, like spikes that dangle off, I think this is the case where it's just not necessarily getting to that location requires parking somewhere too, not just being at the road next to it, right?
That's exactly right. The engine takes into account the speed limits and the traffic patterns. So you can actually configure it to do AM peak, PM peak, midday, etc. And the polygon would actually look different depending on whether you've got a traffic jam out there on McNary Parkway at 5 p.m. The engine's very configurable. You can tell it what you want the ambient off-road speed to be. So if you set it at 35, that means people are going 35 miles an hour as they leave their driveway. Some of my neighbors do that, but maybe not with COVID. These days, everyone stays at home. But you get the idea, and so you get some very interesting patterns as you approach major highways or major roads.
Yeah, as you mentioned that, I do see how those roads are come into play and impact. That's pretty neat to see that.
Yeah, it's a cool question though. The shapes of these polygons is very interesting, I find too, and tweaking those parameters would be, I think, an interesting afternoon on its own, just to try to figure out what's if you're taking this to a prod system, right? You're really trying to build a prod ML model to make real business decisions, right? Tweaking those specifically for your problem, I think, would be very insightful.
Mm-hmm.
Yeah, and Daniel, I presume that you can lock in maybe a snapshot or a date, an effective period where this 5-minute drive time polygon can be consistent for run over run, or comparability sake or planning sake. It doesn't necessarily have to contribute to your very fast update cycles for the things that would impact this thing. If I had a longer term planning horizon, maybe I wouldn't want yesterday's data.
There you go. No, that's a great point, Eric. The reference data that sits behind this is really the US Street Network, and it doesn't, I think we change it quarterly. So you can also just maintain the same reference data for however long you want to keep it there. And at that point, every run you make would come out the same. Yeah.
Cool. All right. I'm glad people are talking. I was a little worried we'd just fly through these notebooks. So cool. All right. So what do we have here? Let's take a look at a histogram of number of locations found in these geofences, and you can see it. There's a bunch, right? There's a lot of accessible addresses for each Starbucks that we've chosen, and a decent spread too. So just some high-level stats. We started with 600 plus geocoded Starbucks. We've got 10 million plus records now after geofencing. So lots of new data we would not have had without the geofencing process. We get nice high precision longitude latitude, and we are calling these the 2 different PB keys. Okay. I think we saw that table. Oh, so here's Geocoded Starbucks. If you remember, right, we had the formatted addresses in lat long and the PB key with an underscore. And the Geofence Starbucks, we kind of streamlined it. Just one Starbucks key to many Geofence keys. And it's a very 10 million plus table rows. And just a quick count, what do we got? 10.5 mil. Okay, so 600 or so Starbucks, 10.5 million locations. That's a lot of information. Okay, so that was a pretty long one. This one's pretty short though. So we're looking at the plan. Where are we now? We want to split this data into residential and business, right? Because the way we construct features for these types of locations will be different. And we want to enable kind of multiple work streams for our team. So here we are, feature engineering. Let's see, what do we got here? Our data is natural separation on geofence locations. Some are business, some are residential. Splitting here on property type. We not only normalize our features a little bit, but we also allow multiple data scientists to build enrichments, aggregations, and model training in parallel. This step is valuable for our team to make more use of our time, but also we can, different people can approach this very differently, and it helps the results with some diversification in there. Okay, so let's see. Let's enrich with property type, right? This, again, I don't know. maybe it's my opinion. I don't know. Maybe other people look at this, but I look at this as kind of the easiest query I can write. Right? This is I select my table, I join on one key, I'm done. Right? I don't know what else you could ask for, but with one quick join on PB key, we're going to grab property type, and we're grabbing it from the address fabric. And we got it, right? This is what, 20-second query for everything. That 10 million plus table, we have property type on every single geofenced location now. So,
and Corey, as I'm going to double click on your comment for folks that are watching with us now and folks that are watching in the future. Look, if you're scratching your head sometimes on the value of getting the agglomeration of or the conglomeration of reference data from Precisely, your comment just made a huge impact of buy versus build. If you had to go out and acquire census demographic, route planning, school, flood zone, on and on and on and on and on data, and maintain just the key structure across those, not to mention the normalization and correction, you'd waste untold number of hours in labor. And you have a select statement with one join on a key, and you're done.
Yep. Yeah, I can't imagine the teams it would take to maintain this much data. Yeah. So yeah, as a data scientist, I don't have to, right? I just use it, right? So thanks, guys. Okay, so we have this table. We just have the formalities here where we persist these into two different delta tables so we can tinker as we wish independently. And just count them. What do we have? It's hard to count for me.
1.5 million.
1.5 million businesses and 8.4 million. Yeah. Yeah. So this is residences and businesses. So cool. More data, and now we've separated things. So now our team can kind of kick into higher gear as well. All right, so where are we now? Let's look at feature engineering for residential. Now these two can get pretty technical. I'm going to probably gloss over a bit of it, but slow me down if something's interesting and you want to talk more. Okay, so our goal now is to take the residential data set we just saved into Delta and build aggregate features on that. So it's kind of a two-step process. One is the step of joining, like we just saw an example where we joined on PB key to figure out the property type. So now we're going to look at more joins onto different data sets to bring in new information, and then we're going to look at some aggregations on those. So residential had over 8 million addresses, so just kind of talking about the data set we're about to look at. We have all kinds of data available here. Some examples are coffee, food, and snacks, consumer spend, consumer specific trends are available in these data sets. So if we're talking about Starbucks, hey, I like that I can see consumer spend on coffee. That's pretty helpful. Additional core demographics, population census, household income was one of our examples, audience profiles. There's a lot here. So just a reminder, our goal is to find things we find interesting, join them to our Geofence data set, and then we'll do an aggregation afterwards, right? Just like we called out earlier. Okay. There's a lot of data sets available. These notebooks are available. I don't want to just bore everybody to death reading through everything here, but feel free to any specific ones you want to call out.
Look at that address fabric. So that's a unique data set. The United States Postal Service recognizes about 155 to 158 million addresses that they can deliver mail to in the United States. What we've done is we've pulled together 11 different sources of address that includes things like undeliverable addresses, vacant lots, crack houses, et cetera, et cetera. And we roll those together and append those to the US Postal Service data, resulting in about 200 million addresses.
Wow.
We roll that, we use it for two things. We use it as the reference data for the geocoders, so you can now find those undeliverable addresses. But we also take and we unroll that into a file that we call the address fabric. So that address fabric theoretically contains every address in the United States, not just deliverable, but every address. And that kind of forms the baseline of what we've done here, Corey, right? Yep. You saw that you did a select out of that address fabric for addresses that fit within the polygons, the drive time polygons. And now to that, you can start joining other things. What makes that so special is that I believe it's the most comprehensive data set for addresses in the United States at this time.
Yeah, wow.
And then, of course, the other 9,000, this is just such a small subset. You thought it was overwhelming. It can be, right? These tables have hundreds of columns, right?
Yeah. Yeah.
But the data that Precisely brings to the table is over 9,000 attributes that describe those locations, and these are just a few of them.
Yep. And even with these few, we'll see here in a minute, when we start joining to some of these tables, I don't know, I think it will be this notebook or the next. And we had so many columns, we just, we can train a model on thousands of columns, or we can say, okay, let's just scale it down. Let's calm down a little bit. So for the sake of going into end, we actually sampled columns randomly to just pick a few. There was a ton there. We specifically chose a few that we knew made a lot of sense, but we also did just some random sampling to see if we could find some gold out there somewhere. Okay, so here we go. Here's example Spark code of just kind of loading up into data frames, many of these different data sets. And let's see, it looks like household, I think 2K is year 2000. I don't have all these column name translations memorized, but for our purposes, we tend to, yeah, you can let the model figure it out most of the time, unless there's a specific thing you're building. If it's not important, the model will say it's not important. Yeah. So, yep, this is really just code to just pull all that. I think this is a list of columns after joining, which is long. There's a lot of columns in here in our feature data, and this is before we do anything special to it. So this is just raw data columns. lots to work with. And you can see in here, there's interesting stuff that, let's see, Pro Bed Bath & Beyond, Pro Best Buy. I think there is even one of these, Pro Bargoer, Casual Dining, Pro Coffee. Yeah, Pro Coffee. That's pretty useful, I'd say, for this little use case we're looking at. Okay, the next thing we do is GeoIDs and census blocks. So a lot of things in these data sets, think about like certain metrics, right, are going to be tied to a census block instead of a particular PB key, right? So what we do here is we really just load in GeoIDs to bring in census block data for every geofence, which is somewhat of an aggregate on its own, and then we'll aggregate on top of those. But this is just kind of a data detail on the way of these aggregations. Okay, a little validation there, and we got our GeoIDs. Okay. So let's do some joins. Let's see, we're going to join audience profile. And GeoIDs equal to code. What do we got? So now for these GeoIDs, we can see Pro Ace Hardware, Pro Apple Store, Pro Bargo, or things like that. And this is the same GeoID many times, you can see, because they're mapping to just similar locations, right? Whether it's not necessarily all the same Starbucks, but you definitely have multiple Starbucks very close to each other. If you've ever been outside and been around Starbucks, there's usually one on every corner. So they'll share these codes sometimes. There's some overlap in some of this data. So what we do here is just more joins, right? The family household income, and we can see we're starting to really accumulate a bunch of columns in this set of data, right? I don't remember all the definitions of all these, but that's okay. Well, the model will figure that out for me. Consumer expenditure. So we can take a look at this. I think, does someone on the call recall what one of these translates to?
Oh, that's I don't.
Damien, I think this was one of yours. Do you remember the expenditure data set? Okay, maybe he's on mute or something. Anyway, it's consumer expenditure, something to do with spending money, right? So we have measures.
Sorry, I was on mute.
Okay.
Yeah. Yes, we're gonna see later in the notebook that there's some of the coffee spend and snack spend.
Mm-hmm.
All these behavioral patterns of consumers.
Cool. Thanks. All right. So continuing, just gloss over census data. We've got some more validation to make sure we're not duplicating things. Okay, so here's what I was kind of mentioning a few times. To quickly explore feature space, we can't just work with everything. So we did a little bit of sampling, a fixed sample size of 5. Basically, for all these giant data sets, let's drop some columns and keep some randomly. What we end up with looks like this. So from audience profile features, there were 61. We kept 5. Pro Macy's, Pro Burger King, Ace Hardware, Pizza Hut, Denny's. From consumer expense, we kept these 5. Not sure exactly what that means anymore, but the docs would tell me if I need to look it up. Anyway, same thing for all these others, where there's how many columns we started with, we kept 5 each. So 193, 56, 172, 244. So total number of features we had available from these data sets that we did join was 730. We're going to keep 29 to do our exploration. All right, so just kind of reiterating that. So now let's do some feature engineering. So census blocks at a small sliver of geography, you can get census data, such as total population by age, sex, race, etc. So block groups generally contain between 6,000 and 3,000 people, with an average usually around 1,500. Census block can be seen as a demographics proxy, right? So instead of, if you guys use Databricks, I have a habit of double clicking on words to highlight, but if you double click on a markdown cell, yeah. Anyway, yeah, so census blocks, so we talked a little bit about that. So let's census blocks per Starbucks location, we're bringing them all together. We can count how many census blocks are in these drive time radii per PB key of Starbucks. All right, so now let's talk more specific. So we did a little bit of random sampling. Let's talk about some specific features we want. So we're talking about Starbucks. So let's decode some of these, right? And I did it again. There we go. Okay. Don't click. All right, so these columns contain spend data, spend in USD on products in the current year. So we can see we've captured tea, coffee, roasted coffee, a lot of things that are specific to the problem we're trying to solve. And these other columns actually contain forecasted demand over the next 5 years on the same categories. So we're bringing in essentially external demand information across relevant industries, but not just Starbucks stores. So even if I was Starbucks, if I worked at Starbucks and I had access to all of our sales data, I would have really cool revenue data that I could help train this whole pipeline, this model on. But this data here is still external to me, right? This is still new information, even if I know how well an existing Starbucks did before. So imagine trying to ask your competitor to hand over a data set, right? Yeah, I'm Starbucks. Hey, Einstein bagels or something. Can you tell me your revenue in each of these areas over the past year? I don't think they're going to go for that. So anyway, cool new data you can bring in to train these models. All right, so we're going to grab these, join them to PB keys. All right, let's talk about audience profiles. I think these are images of these census blocks. Is that right?
Looked like it, yes.
Mm-hmm. And you can actually see that I think this is a precisely image, I think. But you can actually see how the color of a census block is different in morning and night. So these are actually time dependent. They're not static descriptions. Anyway, let's see. Yep, dynamic. Just lots of cool data sets. So we could spend all night just talking about every one of these data sets, but we got to try to move end to end here. So let's see. Per geofence location, let's grab audience profiles. All right, we've grabbed a bunch of stuff. Let's do the aggregation part, the part Eric pointed out. So hey, I don't want that same Starbucks in that table 3 times. I want it there once. I want to collapse this income into an average income. So as we go through this, you can see one of the cool things when you work with a team of developers, you'll see different code styles. So code style here, I actually think this is pretty neat, the way Damien put this one together. So he actually built for every column of data that he's keeping, he's going to compute an average, a standard deviation, a min, and a max, all as new features. So instead of just collapsing income to average income, we're going to collapse the column income into 4 columns: average, standard deviation, min, and max income. So that's 4 features from 1. And here you go. Easy. You just call the aggregation. Spark handles it for you. All right. We also did some work for medians. It's a little bit more involved to get a median. So we used 50th percentile median. And I think we do the same pattern just for a couple of different sets. So let's go through. There's another median. Okay, so at the end of this, we just do a mega join. Luckily, it's a pretty easy mega join because all these tables are only about 500 or 600 Starbucks PB keys each. Oh wait, yes, aggregations are, right? So pretty small tables, they all have the same primary key, so the joins are pretty simple. But yeah, once we got this, here's our, just a whole bunch of columns. And you can see we've, Damien's put on here, this is a median version of that, median version of this column, the standard deviation version of this column, right? So tons of features to train a model on. It's a little sanity check for duplicates, make sure we're safe. Save it to Delta, and let's take a look at it. These are the residential features we've got. And 600 rows, right? Not a ton of Starbucks that we're worrying about right now, but the columns are intense, right? This is a ton of new features you can use thanks to the enrichment. And now we get to throw this at models, right? See what we can learn from it. Okay, I hope we've still got people paying attention. Can I get any feedback on more or less detail from anybody in the call?
I think it's been pretty good for me, the level of detail you've been covering, so thank you.
All right. All right, well, I'll take that as a keep going. Feel free continue any questions or anything. Look, I've got
I love this. You know I love this level of technical specificity, Corey, so keep at it. All
right. I'll keep at it as long as my voice keeps up. 2 hours is a long talk. Anyway, we're good. We got some time. I have a teammate here. So this is, like I said, we had 2.25 people working on this. Javad took, so we just looked at a notebook from Damien where he did the residential feature engineering. Javad did a similar process very differently for business feature engineering. That's why we separated the data sets, and we can just work very independently without stepping on toes. So we recall we had 1.5 million addresses that were property type business. Let's see, we want to look at some kind of features. What, for example, related businesses in the area, employees of related businesses. Let's see how many businesses are in the neighborhood of any type, not just related. How many other Starbucks are nearby? That's a pretty useful data point. Average sales volume of related nearby businesses. So lots of cool features we can get for businesses that are very different features than something like household income, right? So, and then we're going to do the same aggregation into this idea of a proximity summary feature. So very similar process. We join with POI and address fabric. We're loading up some tables, do some joins. I don't want to downplay the work Javad did here, but we just saw something very similar, so I don't want to spend too much time on this. But we can see we've already got a ton of new columns for each of these PB keys. We did some Starbucks specific filtering to learn special things about Starbucks, and then we can aggregate down a lot of these features. Let's see, finding related businesses. So that's an aggregate, right? You want to count instead of just list them all. Number of related businesses, right? We can see for each Starbucks here, 55 related businesses in the drive time polygon, 500, right? Some of these polygons, I guess if you're in a high speed limit area, right? You can have a ton of data in these polygons. Average number of employees of related business, just an interesting feature, right? This would be really tough to get your hands on if you just worked at Starbucks, to have this data for not Starbucks businesses, but related businesses. Let's see. And I did just want to point out, right? So we saw the other one where we had hundreds of columns and we did kind of this deep learning approach of mean, median, min, max, standard deviation columns as features, where Javad's approach here is more, I'm trying to predict star rating, right? I want to know when people go here, are they happy with their service? So this idea of what's the average number of employees at stores like this? I think that's a good intuition there, right? A human intuition of selecting something like number of employees to understand star rating. If you have a small business with a lot of employees, then there's a lot of people helping customers. If you only have, one or two people working at a time, you have upset customers, right? We've all been to Walmart late at night where the lines are really long and there's one register open, right? It's a interesting feature to build for the problem. So yeah, Javad continues with this approach. Number of employees for related businesses. We've got number of all the businesses of any type in the area, and some of these, there's a lot of businesses. Number of all nearby Starbucks. This one blows my mind. Starbucks is just going crazy. Yeah. Okay, let's see. Average sales volume of nearby businesses. So just the fact that you've got some USD measures on sales for businesses is super useful for predicting. Okay, stars maybe less so, but in a realistic scenario where you'd want to model not stars, but say revenue or something, this would be enormous. This would be huge. Value, very valuable. Okay, so then we do a similar process where we do this mega join, combine them all, and we've got, we persist it to delta and we take a look at it. So for the business route, instead of the deep learning, throw a million columns at it, we took the, let's try to construct some specific columns. And this is what we got. Okay, so we've engineered features. This is just a really short one. Just join them back together into our master training data set. Not a lot here, just joining those two tables and we're good. So we have, at the end of the day, we did a little bit of filtering there. If a Starbucks had no, say if a Starbucks had a bunch of residential nearby but no businesses, I don't think that ever happened. But if that happened, we would filter that row out. the opposite probably happen more often, where a Starbucks has many other businesses nearby, but no residentials. So that would mean all the residential features would be null. So we just drop those training examples just to make life easier on the modeling. So we've still got about 600, and this is what it looks like. Lots and lots of training data. Yeah. Features, yeah. So as data scientists, we're very happy at this point. So before I jump into the ML piece, any questions, thoughts, comments, anything? All right.
Well, my observation thus far is that data science takes about an hour and 15 minutes to do all of data engineering up to modeling. Is that about right?
I wish.
No. Okay. All right.
Yeah.
I mean, you've just proven it to me.
I think there's a number. I think Andrew Ng, he's the famous one. Something like 80% of a data scientist's life is actually feature engineering. The best way to make your model better is to engineer better features. So, yeah. All right. So,
Corey, I had a question. You know, as you're going through each of these, the feature engineering, and you're getting these results, you're getting these outcomes. You know, how are you sort of recording those? They're obviously recorded in the notebook, but how are you sort of taking that and then building your story? You know, what does that, the story, the insight? How are you sort of working that into your story?
Yeah, good question. So one way we look at this is here. Every one of these feature sets that we built, we keep them around. So anybody can do kind of SQL analytics on top of these Delta tables to investigate or build additional stories on top of this data after we built. Just kind of Databricks, easy to do, right? You can write a data frame to a table in a one-liner. So we do that, and we keep these features. But for the greater story that we're trying to tell, let's look here again. Let's pull this one up. The story we're after is everything we just looked at falls in this yellow box, right? We're building features because our real goal is to train a model, because our real goal is to pick a location, right? So at the end of the day, all of this feature building stuff is just an effort to make our model a little more accurate. Because the real thing that matters here, the story here, is I need to build a Starbucks. Where should I build it? And instead of having a person look at all those features we built, we're going to build a code that will rank the locations based on information it learned from those features. So bring a little bit of machine learning AI in there. So we aren't people telling the story about household income, but instead we're saying we let a machine learning model learn it way more than I could from those features. And now it can rank all those candidate real estate locations for me.
Thank you.
Good question. Let's see. So let's get into modeling. So we could get real excited and live here for years, but let's not. we know this is a hackathon. We know this is a POC. We know all these other things. Stars are probably not the world's most interesting thing to be great at predicting. So we'll just kind of keep it brief. Do some imports. We're going to grab our feature data. So we persisted this in Delta, so we can just grab it. No big deal. Take a look at it. If you forgot what it was, here it is. We do a little bit of data preparation for the model. So when you use SparkML, which is what was used here, we need to use these vector assemblers. Just transform your feature data a little bit to train models efficiently on with Spark. If you've ever read a data science blog, you've probably seen something like this. We do a split on our data for testing and training. And we kind of arbitrarily, not really arbitrarily, random forests and gradient boosted trees are known for doing really good at this kind of data. But, no fancy tuning here, right? Let's just train 3 different types of models and see where we end up. So we create the models, we do a dot fit, super easy, not spending a lot of time on it. Make predictions on your test data, evaluate all your models here, and let's skip down to the plot. Okay, so we're plotting RMSE and MAPE, so root mean square error and mean absolute percent error. So if you're looking for something intuitively understandable, MAPE is probably your go-to, the blue bar. Mean absolute percent error is I predicted all these locations and what percentage wrong was I for all my predictions. On average, what was my average error there as a percentage? So if it was supposed to be 5 stars and my model predicted 4, my percent error there, absolute percent error, is going to be 20%, right? So if we look at this, the mean absolute percent error it's less than 20%. That's good. It's not much less. Oh, here we go. Random forest. Random forest with no tuning, 17% maybe. So understandable. Not the world's coolest model, but this gives us a direction on, okay, if we're going to do a little bit of hyperparameter tuning, just let Spark, let it rip, come back tomorrow, see what we got. Random forest is probably the one we want to bother with the hyperparameter tuning on. Okay, so keeping that one brief, we'll jump into the grid search. So here we are. So we built the training data, we did all this, we did the rough modeling to get an idea where we would want to do a grid search, and now we're going to do that, the hyperparameter grid search. So here's this picture from the beginning again. What we did is we basically Spark, right? If you create a Spark data frame, and inside that data frame, what we put is it's essentially a parameter grid that we want to search. So every time you train a random forest model, you can tell it how many estimators should you use. You can tell it the criterion, mean squared error. You can tell it the depth 5 or depth 10. So we just build this giant data frame of all the trials we want to test, all the models we want to train, and we just let Spark train. Basically, think of like a UDF, right? We talked about what is a UDF. We want to apply a function to every one of these rows, but our function in this case is train a model based on those parameters. So then we just let all the workers just go to town on this data frame and train in parallel. So yeah, we had 100,000 models, and it is only a few hours to compute, not a tough one. So also MLflow, if you haven't used MLflow before, pretty handy, especially in Databricks. Actually, I think I have it pulled up. Yeah. Every time you train a model, you can log whatever you want here. So you can log your mean absolute error, mean absolute percent error, the parameters you used for training this model, so you can know which one did well and which one didn't. So anyway. So let's go through really quickly how we did that. Let's first thing we do is we grab our features that we built. This is a small data set. So I know people often think Spark and they think big data and data science and all that. Like first things first, you don't need big data to train a model. We have 600 locations to train a model. That's great. But also we don't need like distributed data sets to train a model on for this. Every worker can handle holding this pandas data frame, this entire feature data set. Every worker can fit that in memory easy. It's just 6 rows. So we grab all this as a pandas data frame. Let's see, we did a little bit of standard scaling on this one just because, why not, might help. Standard scaling is, if you remember all the features we had, it'll take too long to load. But if you remember the features we had, some of them were like average household income. That number is definitely in the thousands. And there were some other features that were like no average number of employees at businesses nearby, which is probably 100 or less, right? When you train ML models, it's good that it's better to have all of your features about the same scale, so they're not. So your model doesn't think one is more important than the other. So standard scaling, all it does is basically assume every column is normally distributed, and you just say, hey, I'm gonna subtract the mean and divide by standard deviation, and now all of your columns are really just z-scores. If you remember your stats class, every entry in every column is now just a z-score for that column. So just a little trick that helps modeling sometimes. We do the same train test split. And let's see, and we're gonna train on stars. Define 2 evaluation functions, MAPE and May. Math, don't worry about it if you don't care. So now we make the modeling parameter grid. So this is this data frame. We're just going to build this data frame with itertools product in Python. Just let it handle that for us. So basically say for every parameter we want to let vary in our search, we define the range that it'll vary. So 10 to 50 estimators, 2 different criterion, MSE and MAE. We'll keep this one the same every time. And for max samples, we'll go from 0.1 through what, 0.9, I think. Yeah. So anyway, basically you just create a data frame, Spark create data frame. The data is just the itertools product of all those lists. And you tell it the schema is this, and you end up here. This is every row is a model to train, a different model. They're all going to train on the same data, but they're going to train different models each. We've got, in this example, 700 in this grid. So this is the model training function, super straightforward. You take the parameters as a dictionary. So here's your parameters, turned into a dictionary, and then you just kind of star unpack that as kwargs, keyword arguments for the model itself, and you .fit. Super easy. We go ahead and evaluate them, and we use MLflow to log the metrics, and use MLflow to log what model was it, what are the parameters we're using, and did we scale or not, because we had some runs where we didn't. So if you've never used MLflow, here's logging is one-liners, whatever you want, and to actually create an MLflow connection and experiment is literally just a context. So also pretty cool tools if you haven't used them before. Okay, so to train it, that's all, right? We just use a RDD map and we say, hey, for every row, call my training function, take in the row and take in, everybody uses the same train and test sets. And there you go, you just let it rip, and we wrote down one of the really good models so we could use that later. So that's really the end of we could try really hard and make them, not even really hard. There's a lot we left on the table, right? From a modeling perspective, there's a ton you could do here. But we decided, this is for POC, we have the framework. If we wanted to build more, we have the space to do it now. So any questions on these two ML pieces? All right. Then let's go to the last set. So I see we got 30 minutes left. I'm not worried at all about time because this last set of notebooks literally just mirrors the first set, right? We're going to do the exact same transformations to the real estate data now. Right, if you remember, the first thing you did was the GeoStar process on Starbucks locations. Well, now we're just going to repeat that process on real estate properties that are available for sale. So things we might buy to build a Starbucks. Let's see, yeah, so note here, if you're looking through these in the future, if you've not yet run the first notebook 1.1, then you can't use these yet, but just make sure you run that first. But we are just going to glide over this because the process is the same. In a prod non-hackathon environment, I would say this whole orange box, you would definitely make this a single notebook or orchestrated by a single notebook and parameterized by the data set. But for the hackathon, we just copy pasted cells of code so we can ferment it in fast. But anyway, this does exactly the same geofencing process, but on the real estate data this time instead of on Starbucks. So we'll just kind of glide through here quickly. Get the travel boundaries, and here we go. For the this is the geofenced results for all of the for sale businesses that we identified in Tennessee.
Cool.
So let's see, feature engineering. So we've already done this. let's go ahead and create some features on this new data set. We're going to create exactly the same features we did before, so it's literally copy pasted code. The input this time is just real estate data instead of Starbucks. So again, loading all these precisely tables. Would love to if this mattered in a prod sense, high priority on our team would be to functionalize this, right? But hackathon, we want to kind of work under the same constraints everybody else was in. Try to make it, 2 weeks, get it done. So anyway, all the same stuff. We get into the same aggregating the geofence locations. We can see this is the same code from Damien we pointed out last time, where we're creating these average, standard deviation, min, max, and median for mini columns. But just remember, this is for real estate, not Starbucks. Save it to Delta, and here's what we got. This is the precisely ID, PP key, of an address that is a business type, address zoned for business. It was previously a restaurant, and it is in Tennessee and was currently for sale when we did the query. So there's only 22 locations like that, but now we have all the same features describing the neighborhood around these for sale locations that we have for those Starbucks locations. All right. So I don't think I'm going to click on this one, but it's here. I'm not going to go through it one by one, but it's here. Right? If you're looking through the code later, do the same thing for business features. So here is the join of the two, which is probably familiar from last time. Really short code, a little bit of validation, and we've got, here is our prediction data set. Again, these PB keys are real estate locations for sale. These are all the information we're going to use to try to determine which one's the best property to purchase and build a Starbucks on. Okay. So this is the purpose. The thing we did up to this point was so we could have this inference notebook and make a decision. So, before we do this, any questions on the few I just kind of glossed over? Anything? All right. Then let's go. In a prod environment, so MLflow, if you haven't used it, you not only can log like metrics like MSE, MAPE, and all that, and parameters. You can also, specifically with sklearn, maybe some others, if you train an sklearn model, you can just save the model directly through MLflow. You can just say, hey, here's my trained model, save that to disk somewhere, and if I want it later, I've already got the model trained. We didn't do that just because we knew we were going to train 100,000 models, didn't want to put all those on disk and waste a bunch of space for no reason. So we just kind of said, hey, MLflow, which one's the best one? And we'll just retrain that because it trains in like 5 seconds. We're okay. So here we go, retrain the best model, chosen from the hyperparameters and the MLflow results. Here's the model that did the best. And yeah, let's just recreate it, define the same metrics and see what we got. And this is what MLflow told us. It's pretty decent. And then let's score the real estate data. So we go to Delta, say, hey, give me the real estate features as a pandas data frame. And we're going to, let's see, with PB key and without. So we just got both. To predict, we just give it the features. We pass that to our model, our random forest regression, predict on the features. We've already trained it. This is what we get for the top 3 scored Starbucks, or, well, they're not 5 stars, but hey, you know, maybe that says something about the property that's for sale right now. But yeah, the top 3 ranking of the 22 were all in the low to mid 3-star rankings. And we can see the PB keys of the winners. I think that was just, probably doesn't need to still be there. Sorry, guys. So let's look at the address of the winners. And we can see just as a little data frame here. Here's the PB key. Here's the precisely formatted, cleaned addresses. We've got lat longs of the winners. And we've got prices, which we brought in, and score. here's the model predicted star rating. We can sort like that. Yeah. So first thing I notice as a human looking at this table, this is the highest star rating, but it's almost 3 million bucks. This one down here is incredibly cheap, a very similar star rating predicted. So as a person who's looking to purchase real estate, there's more to the equation than just star rating, right? So you could do ILMIL on this layer too if you wanted. Let's not go down that rabbit hole today. But just as a person, you know, kind of finalizing, we wanted to drive a decision here, right? With the data we have here, what decision would that be? So we said, okay, we've got these clean addresses. Let's toss them into a map program. Let's take a look at them, right? Let's pretend we're going to go visit these sites and look at what we're looking at. The first one was very interesting. This looks like an old house to me, but this still got predicted. This is a cheap one. 150,000 bucks. You could buy this. It is zoned for business. It was previously a restaurant, and if you we got on Google Maps and looked around. Across the street is another house similar to this, and it's, I think, Grandma's Cookies or something is what it was called. So it's right next to
Grandma Desserts.
Grandma does this thing. Yeah,
It's the most popular desserts in the whole area.
Yeah, but the interesting thing is, right across the street, right, we're thinking, hey, theoretically, let's build a Starbucks somewhere. And to be fair, if Starbucks bought this, they'd tear this down and build something else. But right across the street is desserts. So it's a very similar type store, which is doing well in this area, as kind of the same kind of product as Starbucks. I thought that was just an interesting, happy little coincidence. Hey, maybe you have a deal, right? They go buy a cookie from Grandma and they come buy a coffee from Starbucks. Cool. The second one we looked at was here, which kind of is perfectly suited for a Starbucks. It's a lot more expensive to buy, but it's a spot in a strip mall. So the fact that this rates pretty highly for stars makes a lot of sense to me. And honestly, I could convince myself, being right across the street from that Grandma's Bakery thing, she probably has really good star ratings too. So anyway, just a cool little, let's finalize all this kind of really quick, train a model, all this stuff. What are we actually looking at as a decision? And it's between these two. I think I'd lean here because it feels safer, but I'd be curious what Starbucks would think of something like that. Anyway, I think that is it. We've gone through all the notebooks, some of them faster than others, but that's the end to end. That's not the prod process, but that's the end to end for sure.
That's pretty cool. Oh.
Thanks so much, Corey, for walking through all that. I'm going to pass it on to Eric to wrap up things for us.
Yeah, right on. Hey, that was a masterclass. Corey and team, I know you had an enormous amount of help with your team. Your team is brilliant. And thank you again to Precisely and the tech resources that you brought to bear in prep for the hack, and of course this event. Look, I know predicting star ratings is silly. It's star ratings is just something for us to bite onto. And I hope everybody got the point, right? That once I start with a piece of information I have in my company or I have readily available, in this case, Starbucks locations, and we got some data from online reviews, great. Just going through the number of features, the amount of data that you can extend and create by way of the geo process with Precisely data is mind-boggling. As I was watching Corey work, just these correlations, whether they're causation or not, just the correlations alone to whether or not I'm a Bed Bath & Beyond consumer, or I like to golf, or I have 2.3 kids, or I drive an SUV, and if that drives my tendency to rate an individual or shop or patronize an individual store is amazing. And we've just scratched the surface. with what these analytics can perform. We haven't gotten into too long. We don't have enough time. So I hope everybody got out of this what they wanted to get out of it. We've got a couple of minutes left. I know it's the evening. I would be remiss if I didn't do a good shout out. Corey heads our data science team, and he's got an amazing group. We would love to talk with your firm about opportunities. I know Precisely feels the same way. So I'll shut up, turn any other final thoughts over to Daniel. And again, great job, Corey.
Thank you. Thank you. Yeah, Corey, you make us look good. I like to say that with all that data and the processing that we do, we try to simplify training models, finding data, building out everything that you need to build valuable features, and you made it look really simple. Keep in mind, there's a lot more out there. So we've recently added mobile trace data. We also have dynamic weather, and we've added a dynamic demographics product as well. So as you train your models, if you're interested in changes, you can actually make direct calls from inside a Databricks notebook to say, hey, this strip center looks kind of yicky. What do you have for me today based on information that I've pulled together? So anyway, we're constantly evolving, as I'm sure you are. And I really appreciate all the work that your team has put into this.
Well, hey, thanks for the opportunity, guys. It's fun code to write, fun problem to tinker around with, and SDKs were a breeze, new data sets we never could have imagined. So thanks for everything.
Well, I'm going to join in on the thank you train, but I just want to say thank you guys all for all the effort you put into this. And I really hope everyone listening in on this is learning a lot. And I know we'll be having this link to share with anyone if you want to share with your coworkers, to share some of the cool things you've learned, or maybe it's someone you know who's having a very similar problem to what Corey has shown so many different solutions to. We ask that you will let us know. We're happy to connect with them and show them a demo and over a quick call, maybe even 30 minutes. I'm sure Corey, Dan, Eric would love to hop on that call and give you guys a demo. But thank you guys so much for joining, and we hope you enjoy the rest of your day.
Thanks, everybody.
Bye, everyone.
Bye-bye. Thank you.
Bye.